ALOHAnet, also known as the ALOHA System, or simply ALOHA, was a pioneering computer networking system developed at the University of Hawaii. ALOHAnet became operational in June, 1971, providing the first public demonstration of a wireless packet data network. The ALOHAnet used a new method of medium access and experimental ultra-high frequency for its operation, since frequency assignments for communications to and from a computer were not available for commercial applications in the 1970s. But even before such frequencies were assigned, there were two other media available for the application of an ALOHA channel: Euro cables and satellites. In the 1970s, ALOHA random access was employed in the widely used Ethernet cable-based network and then in the Marisat satellite network. In the early 1980s, frequencies for mobile networks became available, and in 1985 frequencies suitable for what became known as Wi-Fi were allocated in the U.S. These regulatory developments made it possible to use the ALOHA random access techniques in both Wi-Fi and in mobile telephone networks. ALOHA channels were used in a limited way in the 1980s in 1G mobile phones for signaling and control purposes. In the late 1980s, the European Standardization Group (GSM), who worked on the Pan-European Digital Mobile Communication System (GSM), greatly expanded the use of ALOHA channels for access to radio channels in mobile telephony. In addition, SMS message texting was implemented in 2G mobile phones. In the early 2000s, additional ALOHA channels were added to 2.5G and 3G mobile phones with the widespread introduction of GPRS, using a slotted ALOHA random access channel combined with a version of the reservation ALOHA scheme first analyzed by a group at BBN. Overview: one of the early computer networking designs, development of the ALOHA network was begun in 1968 at the University of Hawaii under the leadership of Norman Abramson and others. The goal was to use low-cost commercial radio equipment to connect users on Oahu and the other Hawaiian islands with a central time-sharing computer on the main Oahu campus. The original version of ALOHA used two distinct frequencies in a hub-star configuration, with the hub machine broadcasting packets to everyone on the outbound channel, and the various client machines sending data packets to the hub on the inbound channel. If data was received correctly at the hub, a short acknowledgement packet was sent to the client. If an acknowledgement was not received by a client machine after a short wait time, it would automatically retransmit the data packet after waiting a randomly selected time interval. This acknowledgement mechanism was used to detect and correct for collisions created when two client machines both attempted to send a packet at the same time. ALOHAnet's primary importance was its use of a shared medium for client transmissions. Unlike the ARPANET, where each node could only talk directly to a node at the other end of a wire or satellite circuit, in ALOHAnet all client nodes communicated with the hub on the same frequency. This meant that some sort of mechanism was needed to control who could talk at what time. The ALOHAnet solution was to allow each client to send its data without controlling when it was sent, with an acknowledgement retransmission scheme used to deal with collisions. This approach radically reduced the complexity of the protocol and the networking hardware, since nodes do not need negotiate who is allowed to speak. This solution became known as a pure ALOHA, or random access channel, and was the basis for subsequent Ethernet development and later Wi-Fi networks. Various versions of the ALOHA protocol also appeared later in satellite communications, and were used in wireless data networks such as ARDIS, Mobitex, CDPD, and GSM. Also important was ALOHAnet's use of the outgoing hub channel to broadcast packets directly to all clients on a second shared frequency, using an address in each packet to allow selective receipt at each client node. The ALOHA protocol, pure ALOHA. The first version of the protocol was quite simple: if you have data to send, send the data. If, while you are transmitting data, you receive any data from another station, there has been a message collision. All transmitting stations will need to try resending later. Note that the first step implies that pure ALOHA does not check whether the channel is busy before transmitting. Since collisions can occur and data may have to be sent again, ALOHA cannot use 100% of the capacity of the communications channel. How long a station waits until it transmits, and the likelihood a collision occurs are interrelated, and both affect how efficiently the channel can be used. This means that the concept of transmit later is a critical aspect. The quality of the back-off scheme chosen significantly influences the efficiency of the protocol, the ultimate channel capacity, and the predictability of its behavior. To assess pure ALOHA, we need to predict its throughput, the rate of transmission of frames. First, let's make a few simplifying assumptions. All frames have the same length. Stations cannot generate a frame while transmitting or trying to transmit. The population of stations attempts to transmit according to a Poisson distribution. Let T refer to the time needed to transmit one frame on the channel, and let's define frame time as a unit of time equal to a T. Let G refer to the mean used in the Poisson distribution over transmission attempt amounts, that is, on average, there are G transmission attempts per frame time. Consider what needs to happen for a frame to be transmitted successfully. Let T refer to the time at which we want to send a frame. We want to use the channel for one frame time beginning at T, and so we need all other stations to refrain from transmitting during this time. For any frame time, the probability of there being K transmission attempts during that frame time is. The average amount of transmission attempts for 2 consecutive frame times is 2G. Hence, for any pair of consecutive frame times, the probability of there being K transmission attempts during those 2 frame times is. Therefore, the probability of there being 0 transmission attempts between TT and T plus T is. The throughput can be calculated as the rate of transmission attempts multiplied by the probability of success, and so we can conclude that the throughput is, vulnerable time equals 2T. The maximum throughput is 0.5/E frames per frame time, which is approximately 0.184 frames per frame time. This means that, in pure ALOHA, only about 18.4% of the time is used for successful transmissions. Another simple and mathematical way to establish the equation for throughput in pure ALOHA is as follows. Consider what needs to happen for frames to be transmitted successfully. Let T represents the frame time. For simplicity we assume that the contention begins at T equals 0. Then if exactly one node sends during interval T equals 0 to T equals T and no node tries between T equals T to T equals 2T, then the frame will be transmitted successfully. Similarly during all next time intervals T equals 2n T to T equals 2n plus 1, T, exactly one node sends and during T equals 2n plus 1, T to T equals 2n plus 2, T no node tries to send where n equals 1, 2, 3. Then the frames are successfully transmitted. But in pure ALOHA, the nodes begin transmission whenever they want to do so without checking that what other nodes are doing at that time. Thus sending frames are independent events, that is, transmission by any particular node neither affects nor is affected by the time of start of transmission by other nodes. Let G be the average number of nodes that begin transmission within period T. If a large number of nodes are trying to transmit, then by using Poisson distribution, the probability that exactly X nodes begin transmission during period T is. Therefore the probability that during any particular period from T equals 2n T to T equals 2n plus 1, T, exactly one node will begin transmission is. And the probability that during any particular period T equals 2n plus 1, T to T equals 2n plus 2, T, no node will begin transmission is. But for successful transmission of a frame, both the events should occur simultaneously. That is during period T equals 2n T to T equals 2n plus 1, T, exactly one node begins transmission and during T equals 2n plus 1, T to T equals 2n plus 2, T no node begins transmission. Hence the probability that both the independent events will occur simultaneously is. This is the throughput. By throughput we mean the probability of successful transmission during minimum possible period. Therefore the throughput in pure ALOHA. Similarly for slotted ALOHA, a frame will be successfully transmitted, if exactly one node will begin transmission at the beginning of any particular time slot. But the probability that one node will begin during any particular time slot is. This is the throughput in slotted ALOHA. Thus, slotted ALOHA. An improvement to the original ALOHA protocol was slotted ALOHA, which introduced discrete time slots and increased the maximum throughput. A station can send only at the beginning of a time slot, and thus collisions are reduced. In this case, we only need to worry about the transmission attempts within one frame time and not two consecutive frame times, since collisions can only occur during each time slot. Thus, the probability of there being 0 transmission attempts in a single time slot is. The probability of k packets is. The throughput is. The maximum throughput is 1/e frames per frame time, which is approximately 0.368 frames per frame time, or 36.8%. Slotted ALOHA is used in low data rate tactical satellite communications networks by military forces, in subscriber-based satellite communications networks, mobile telephony call setup, set-top box communications and in the contactless RFID technologies. Other protocol, the use of a random access channel in ALOHAnet led to the development of carrier sense multiple access, a listen before send random access protocol that can be used when all nodes send and receive on the same channel. The first implementation of CSMA was Ethernet. CSMA in radio channels was extensively modeled. The AX25 packet radio protocol is based on the CSMA approach with collision recovery, based on the experience gained from ALOHAnet. ALOHA and the other random access protocols have an inherent variability in their throughput and delay performance characteristics. For this reason, applications which need highly deterministic load behavior sometimes used polling or token passing schemes instead of contention systems. For instance, ARCNET was popular in embedded data applications in the 1980 network. Design, network architecture. Two fundamental choices which dictated much of the ALOHAnet design were the two-channel star configuration of the network and the use of random accessing for user transmissions. The two-channel configuration was primarily chosen to allow for efficient transmission of the relatively dense total traffic stream being returned to users by the central time-sharing computer. An additional reason for the star configuration was the desire to centralize as many communication functions as possible at the central network node, minimizing the cost of the original all-hardware terminal control unit at each user node. The random access channel for communication between users in the mean Hyun was designed specifically for the traffic characteristics of interactive computing. In a conventional communication system, a user might be assigned a portion of the channel on either a frequency division multiple access or time division multiple access basis. Since it was well known that in time-sharing systems, circa 1970, computer and user data are bursty, such fixed assignments are generally wasteful of bandwidth because of the high peak-to-average data rates that characterize the traffic. To achieve a more efficient use of bandwidth for bursty traffic, ALOHAnet developed the random access packet switching method that has come to be known as a pure ALOHA channel. This approach effectively dynamically allocates bandwidth immediately to a user who has data to send, using the acknowledgement retransmission mechanism described earlier to deal with occasional access collisions. While the average channel loading must be kept below about 10% to maintain a low collision rate, this still results in better bandwidth efficiency than when fixed allocations are used in a bursty traffic context. Two 100 kHz channels in the experimental UHF brand were used in the implemented system, one for the user-to-computer random access channel and one for the computer-to-user broadcast channel. The system was configured as a star network, allowing only the central node to receive transmissions in the random access channel. All user TCUs received each transmission made by the central node in the broadcast channel. All transmissions were made in bursts at 9600 bits, with data and control information encapsulated in packets. Each packet consisted of a 32-bit header and a 16-bit header parity check word, followed by up to 80 bytes of data and a 16-bit parity check word for the data. The header contained address information identifying a particular user so that when the mean Hyun broadcast a packet, only the intended user's node would accept it. The mean Hyun, the central node communications processor, was an horsepower 2100 mini-computer called the mean Hyun, which is the Hawaiian language word for a Euro or Impa Euro, or dwarf people, and was named for its similar role to the original ARPANET interface message processor, which was being deployed at about the same time. In the original system, the mean Hyun forwarded correctly received user data to the UH central computer, an IBM System 360/65 time-sharing system. Outgoing messages from the 360 were converted into packets by the mean Hyun, which were queued and broadcast to the remote users at a data rate of 9600 bits. Unlike the half-duplex radios at the user TCUs, the mean Hyun was interfaced to the radio channels with full duplex radio equipment. Remote units. The original user interface developed for the system was an all-hardware unit called an ALOHAnet terminal control unit, and was the sole piece of equipment necessary to connect a terminal into the ALOHA channel. The TCU was composed of a UHF antenna, transceiver, modem, buffer and control unit. The buffer was designed for a full line length of 80 characters, which allowed handling of both the 40 and 80 character fixed-length packets defined for the system. The typical user terminal in the original system consisted of a teletype Model 33 or a dumb CRT user terminal connected to the TCU using a standard RS-232C interface. Shortly after the original ALOHA network went into operation, the TCU was redesigned with one of the first Intel microprocessors, and the resulting upgrade was called a PCU. Additional basic functions performed by the TCUs and PCU A01 trademark S were generation of a cyclic parity check code vector and decoding of received packets for packet error detection purposes, and generation of packet retransmissions using a simple random interval generator. If an acknowledgement was not received from the mean Hyun after the prescribed number of automatic retransmissions, a flashing light was used as an indicator to the human user. Also, since the TCUs and PCU A01 trademark S did not send acknowledgements to the mean Hyun, a steady warning light was displayed to the human user when an error was detected in a received packet. Thus it can be seen that considerable simplification was incorporated into the initial design of the TCU as well as the PCU, making use of the fact that it was interfacing a human user into the network. Later developments. In later versions of the system, simple radio relays were placed in operation to connect the main network on the island of Oahu to other islands in Hawaii, and mean Hyun routing capabilities were expanded to allow user nodes to exchange packets with other user nodes, the ARPANET, and an experimental satellite network. More details are available in the technical reports listed in the further reading section below. References. Further reading, Stallings, William. Data and Computer Communications. Macmillan PPA 296 302. ISBN A0-02-415451-2 R. Metcalf, Xerox PARC memo, from Bob Metcalf to Alto ALOHA Distribution on Ether Acquisition, May 22, 1973. A binder, ALOHAnet Protocols, ALOHA System Technical Report, College of Engineering, The University of Hawaii, September, 1974. A binder, W. S. Lee and M. Wilson, The ALOHAnet Mean Hyun Euro Version 2, ALOHA System Technical Report, College of Engineering, The University of Hawaii, September, 1974. N. Abramson, The ALOHA System Final Technical Report, Advanced Research Projects Agency, Contract Number NAS 2-6700, October 11, 1974. N. Abramson. The Throughput of Packet Broadcasting Channels, IEEE Transactions on Communications, Vol 2501, pp 117 128, January 1977. M. Schwartz, Mobile Wireless Communications, Cambridge University Press, 2005. K. J. Negus, and A. Petrick, History of Wireless Local Area Networks in the Unlicensed Bands, George Mason University Law School Conference, Information Economy Project, Arlington, Virginia, USA, April 4, 2008. External links, Dynamic Sharing of Radio Spectrum, A Brief History, Funding a Revolution, Government Support for Computing Research, ALOHA to the Web, Norman Abramson, HICCS Distinguished Lecture.